Monday, May 20th, 2013. Forecasters at the Storm Prediction Center in Norman, Oklahoma, dial in their forecasts over their own homes as conditions align for an explosive weather day. Within a highlighted moderate risk, a 10% hatched tornado probability is denoted through Oklahoma. Even with this elevated risk, little did anyone think central Oklahoma would see weather history repeat itself. My name is Ethan Moriarty. I'm a mechanical engineer by training with a fascination in tornado damage forensics. This is a damage analysis of the 2013 Moore, Oklahoma EF5. Thank you for tuning in to this installment of the Damage Analysis series here on the June 1st YouTube channel. If this is your first time joining us, this is a series where we dive into the historical tornadoes of our past and take a look from an engineering perspective at the damage that they cause and break down the physics at play. To start, we'll go over some of the statistics from the tornado, break down the weather side of the equation, and then dive into the damage analysis itself. As stated earlier, the Moore 2013 EF5 took place on May 20th, 2013 in central Oklahoma. This tornado was on the ground for 13.8 miles over the course of 39 minutes. The tornado peaked out at a max width of 1,900 yards, which is just over a mile wide. In terms of a human impact, this tornado was about as bad as it could be, with 24 confirmed fatalities and 212 reported injuries. As I've mentioned previously, injuries are a statistic that are not to be taken lightly, as severity of injuries can range from an overnight hospital stay to life-altering injuries, including head trauma, spinal cord injuries, or even amputations. So it's important to keep in mind that 212 is a very significant number. The official rating of this tornado on the Enhanced Vegeta scale by the National Weather Service and engineering surveyors marked this tornado as an EF5 with estimated peak winds of 210 miles per hour. It is also worth noting, at the time of recording this video, this was the last EF5 to have taken place in the continental United States. Diving into the weather side of the equation behind this tornado, the system at large that was responsible for this tornado started with an upper level low over the northern plains of the United States. Associated with this upper level low was a giant digging trough that ejected across the southern plains and up through the Midwest. Moisture was abundant in the southern plains on this afternoon, with dew points reaching into the upper 60s and in some places even over 70 degrees Fahrenheit. Associated with the strong surface low over the Dakotas was a stationary front that draped its way from the origin of the surface low down through Texas. Throughout the day on May 20th, there was an advancing dry line from western Texas that moved eastward into Oklahoma and eventually created a triple point over the localized low over the central Oklahoma region. A special midday weather balloon sounding was launched in central Oklahoma. This sounding revealed that there was over 3,000 joules per kilogram of mixed layered CAPE, as well as 5,000 joules of surface-based CAPE. The instability over central Oklahoma was rapidly growing, and the cap was quickly eroding away. Storms fired off the dry line a little after noon, and the storm that was closest to the boundary ultimately became the producer of the Moore EF5. Now that we've gone over the tornado stats as well as the overall weather picture of that day, let's dive into the path itself and get an overarching look at the damage that was caused by the Moore EF5. Here I am quickly just zoomed out over the entire path. This one is relatively short in some of the high impact tornadoes that we've looked at previously. Some of them span, 60 miles. This one's only 13, 14 miles in length. And it is worth noting, due to the fact that this went through an extremely heavily populated area, there are well over 4,000 damage indicators in this path. So I have filtered a lot of the lower rated damage indicators out and left a lot of the EF4, EF5, and some of the unknown damage indicators in here because the sheer quantity of damage indicators is overwhelming. This goes into how the survey was conducted. And this survey was an extreme undertaking. It required both ground survey teams and aerial survey teams. So you had a lot of people on the ground looking at the highest impact damage indicators, and then a lot of aircraft involved that were kind of mapping the overall picture and a lot of the lesser damage indicators. So a lot of like the EF1s and 2s, that type of stuff, were done through the aerial surveys. So it's not like there was a ground team that was reviewing those. They were focused on the heavily impacted damage indicators, if that makes sense. Of course, after natural disasters, the natural human urge is to clean up a lot of the damage. So the survey team had a lot of data that they had to try to take in before people started really manipulating the scenes. So you have to give these people credit for being able to document this huge amount of data in such a short period of time. It is by no means perfect, but it is a nearly impossible task to begin with. So you have to take a lot of that in mind when we're looking at a survey that goes through a heavily populated area like the southern OKC metro. Zooming in here to the first damage indicators, which happen in the northern section of Newcastle, Oklahoma. The tornado started just along Oklahoma 37 here and strengthened quickly, as we already have a EF4 damage indicator within the first, kilometer of the path, I would say. Worth noting, from the original origin point of the tornado to by the time it takes its first real right turn, when that storm really latches on to the boundary at play, you can see how quickly it widened out in the initial phase of the tornado. So, you went from the initial ground contact to almost peak width within, a couple miles. So that's something that goes to show that this tornado matured very rapidly and was already at its peak strength basically before even entering the populated region of southern Oklahoma City and more. In the southern Oklahoma City region of the tornado before it enters the town of Moore, there are a number of EF4 damage indicators and several interesting pieces that we're going to dive into a little bit more in depth of damage, including origin points of fuel tanks that were thrown in some instances over a mile. So, we're going to look into what it would take to loft a fuel tank of that size, because fortunately we have geometry that they gave in the survey, and as well as the weight. So that's really useful and makes our lives a lot easier. So we can look into what it would take to throw something of that nature such a far distance. Moving into the Westmore neighborhood of southern Oklahoma City, this is where the Briarwood Elementary School was impacted, and some of the resting places of the fuel tanks that we were talking about earlier ended up being left behind. And then through the Westmore neighborhood is some of the most intense damage of the tornado, including our first EF5 level damage indicators that were in the path of this tornado. It is worth noting that there are only 9 EF5 damage indicators in the entire path out of I think there's over 4,900 DIs in this damage path. That just goes to show how stringent the criteria is for an EF5. And, there's a good report on the survey and the damage overall that kind of lays the groundwork of what constitutes an EF5 damage indicator that I think is important to get into, but we'll get to that as we move eastward here. For the meantime, And just, I mean, I think it goes without saying that the sheer amount of debris that is in this path is just overwhelming. And it is very hard to comprehend, and I'm not quite sure how to fully realize it. You know, I've been looking at tornado damage for a while now, and it is still hard to visualize. I've never seen EF5 damage. The most intense damage I've seen personally in person is EF3, and EF3 is quite overwhelming. So to have an EF5 tornado through such a populated area is both gut-wrenching, pulls at the heartstrings, and is just overall depressing and hard to really materialize, to be completely honest, and really wrap your head around that something could be this powerful. As we move into the town of Moore, we pass the Plaza Towers Elementary School, which saw 7 fatalities at the school, which is honestly the most tragic part about this tornado, in my opinion. I mean, obviously, any loss of human life is tragic, but particularly at a school, that is really, really hard to deal with. And it's, you know, one of the saddest parts about this tornado. I mean, there's really no words that really can be put to it, to be completely honest. The tornado would continue northeast again before executing almost like a loop style turn. I wonder if the storm cycled, or there was some sort of occlusion handoff type of thing between mesocyclones of the tornado. I'm not really sure. I'm not a meteorologist, so I don't really have a good explanation as to why there was this sudden kind of shift in direction that brought this tornado back in an easterly trajectory versus a northeast trajectory. But I think it's worth noting that because the tornado stalled out here, there's a string of 5 EF5 damage indicators here. And arguably, I think these are the most conclusive EF5 damage indicators in the path, if you ask me. And it probably has to do with the fact that the tornado spent the most time as it executed this kind of maneuver over these houses. So it's no surprise that there was a concentration of EF5 damage indicators. There's also the gas station and convenience store that's up here in the corner that there were 3 fatalities at. And then eventually, as it jogged back to the southeast here, it impacts the Moore Medical Center, where cars were thrown all over the place, mostly in the southeasterly direction. And it's also noted in the survey that 1 car was found on top of the Moore Medical Center on a 2-story section of it. So, you know, I think it goes without saying that an EF5 tornado is going to be throwing cars quite the distance. So it's completely within the realm of possibilities to have a vehicle that ends up on a roof. The tornado then continues east over Interstate 35 and eventually makes its way into the eastern half of Moore. We still have damage indicators that are exceeding EF4. There's a couple more instances of EF5 along the track. But I think it's interesting here that the tornado kind of thins out a bit as it reaches this eastern portion of Moore. As you can see over here in the southern OKC region by the Briarwood Elementary School, there was a much wider swath of damage, even to the EF0 extent, versus what's happening here in eastern Moore. Just something interesting. I wonder if that has to do with the cycling of the storm as a whole or something along those lines, but I just think it was worth mentioning that the width of the tornado actually kind of decreases towards the end of the path here. As the tornado finishes its way through Moore, it's still at very high intensity with, you know, a couple more EF5 damage indicators before finally reaching the outer limits of Moore and beginning to rope out and dissipate. Now that we looked at the damage path as a whole and kind of get a sense of where the damage was and where the key landmarks are, let's establish what the criteria was for an EF5 damage indicator. The criteria for an EF5 in the case of the Moore 2013 EF5 is spelled out in the official report of the damage survey, which is written by Donald Burgess as well as engineers like Tim Marshall. In the report, there are 4 criteria for a damage indicator to be signed in EF5. Reading directly from the report, let's look at the 4 criteria in depth. Number 1, foundation swept clean with debris strewn some distance downwind. 2, foundation generally slab to base plate connections with properly spaced bolts with properly fitted, sized, and tightened washers and nuts. 3, removal of large percentage of those base plates from the foundation. And 4, anchor bolts that have been bent, which means that the frame had transferred the wind load into the foundation base plate connections. The reason why some of this criteria was spelled out in the report is so that there was an equal measure to compare this to the May 3rd, 1999 event, which obviously was the landmark event for a high-impact tornado in the OKC metro area. In the time between the 1999 tornado and the 2013 tornado, there was a lot that has been learned with how damage behaves in tornadoes, particularly how homes are constructed and the importance of construction quality. In this report, they noted the decrease of how many homes were actually assessed in EF5 Damage Indicator versus an F5 in 1999. In the 1999 damage survey, of all of the damage indicators, only 1.1% of them were of the F5 category. In the case of the 2013 Moore tornado, there were only 9 damage indicators assigned to EF5, which came out to a percentage of the total damage indicators surveyed of 0.4%. Another reason why this extra criteria was established for an EF5 damage indicator was so that surveyors can definitively on the spot mark it as an EF5 without any need to try to find, connection methods or anything like that. It was very evident right there just from looking. You could see the bent anchor bolts and you weren't hunting for connections that may have never been there, those kind of things. So that's why the EF5s were so few and far between in this damage survey. The strict criteria made it impossible to say that it was anything less than an EF5. Before we get all up in arms in terms of the definition of what should be and what should not be an EF5 damage indicator, I think it's important that we take a look around Plaza Towers Elementary School and uncover something that is a little alarming in the grand scheme of things. If we zoom in here to around the Plaza Towers Elementary School, we notice that there are a lot of very destroyed houses along the path here, but only a couple of them are actually rated EF4. Remember that I filtered a lot of the lower level damage indicators out just to kind of clear things up in terms of being able to actually digest some of the information so it's not just a huge swath of colors. And there is a reason to that. In the wake of the May 3rd, 1999 tornado, building codes were updated for a lot of the communities in the OKC metro area in order to prevent another tragedy of that magnitude from happening again. What is alarming about this is that most of the homes that are around the Plaza Towers Elementary School were built after the May 3rd, 1999 tornado. In theory, these homes should be built to the highest standard as there were building codes put in place in order to make these houses as strong as possible against an event like this. Unfortunately, what was found during the survey is that many of these homes did not have adequate anchoring techniques utilized in the building of these homes, meaning that they weren't even able to sustain EF4 damage before completely blowing away. So a lot of these houses could only be rated EF3 due to the poor anchoring techniques. Even though the 2013 Moore tornado is one of the strongest tornadoes on record, it highlighted the construction flaws that were a part of much of suburban Oklahoma in the wake of an event that, in theory, should have rectified a lot of the issues that were already found. I just thought it was really important to bring that up as it was a main highlight in that damage report. It's linked down below for more details if you want to read up. Let us now dive into the propane tanks that were found thrown over a mile and see what it would take in order to throw something of that size and weight a significant distance. Here we are just east of the Briarwood Elementary School, where we have this unknown damage indicator which shows one of the propane tanks that was thrown from the farms further west. To start off, let's establish the geometry of the tank. It is 30 feet long with a diameter of 8 feet, and it weighed 10 tons according to the details in the damage indicator survey text field. To figure out how much wind force it would take to overcome the force due to gravity, we're going to compare it via a sum of moments. So once again, we'll pick a point where there's going to be a moment, and then we basically take the distances from that moment from where the forces are applied in order to kind of balance out the forces and then compare the two. So fortunately in this case, because it's just a cylinder and we're putting the tipping point at the same distances on either side, the two distances just cancel each other out, as they're both just the radius from the center of gravity of the tank. So ultimately, it's pretty straightforward. We just compare the force of drag equation that we like to use with the weight of the tank and set that force of drag equation equal to the weight, and using the geometry as well as the coefficient of drag of a cylinder, we were able to kind of build an approximate model in order to solve for the wind velocity that it would take to overcome that force due to gravity. Ultimately, in this simplified case, it comes out to 307 feet per second or 209 miles per hour, which it makes total sense given that the rating of this tornado was at peak estimated wind speeds of 210 miles per hour. Keep in mind, these mathematical equations are completely idealized and simplify a lot of the geometries. So, obviously there's going to be some give or take with a lot of these numbers, a plus or minus tolerance, if you will. But nonetheless, to throw a 10-ton tank over a mile, it's going to take a considerable wind speed. And I think it's safe to say, even though it is rated as an unknown damage indicator because it doesn't fall within the standard enhanced Vegeta scale guidelines, just from this simple analysis alone, I think it's safe to say that it's capable of being an EF5 damage indicator. Another unknown damage indicator that we can take a deeper in-depth math dive into is this Billboard over here, which didn't have an official rating by any means. It's another one of those unknown damage indicators, so I figured we'd take the time to evaluate it and figure out what kind of wind speed it would take to knock over a billboard. Something tells me that it wasn't going to be, an EF5 level echelon given the surface area of the billboard, but I wanted to break down the math behind it in order just to kind of show the science behind it and how we can kind of derive and figure some of these things out without the, guidebook to the enhanced Vegeta scale. If you watched my rolling fork EF4 analysis video, this is very similar setup to how we analyzed the water tower. So we have a giant central column, the big cylinder that's supporting the billboard, and then the billboard itself. Both of these we're going to separate into their own separate bodies, if you will, each having their own weight vector. That way we can break up the moments about the base of the billboard, so we can measure the wind force to the center of both of those objects and use their appropriate coefficients of drag, as the two different shapes have very different coefficients of drag. Looking at the base of the tower here, this is where we have that failure point. It pretty much succumbed to the wind force due to a bending moment. So we're going to use our bending moment equation and compare that alongside the failure criteria for steel, which is the material used in the central column for billboard. After getting the weights, we have to find the normal axial stress that's taking place due to the weight of both the cylinder and the billboard. This way we can add a little bit more margin to the failure criteria, as that compressive stress is actually counterbalancing the tensile stress that is ultimately responsible for the failure. So because steel's yield is at 30,000 psi, this additional 260 psi from the weight can be added to it, as it's a compressive force that is counteracting the tensile load that's trying to tear it apart. In our bending moment stress equation, we have the distance to the central axis, which basically, in the center of the shape, the further out you go, the more that it's going to play a factor into the failure of the material. That bending moment is going to get larger and larger the further out in the material you go, so the failure is going to be at that outermost fiber. And then finally, there's the area moment of inertia, which takes into account the shape of the object that the bending moment is going through. So in the case of this giant steel tube, it's a giant hollow cylinder. So we solve using the area moment of inertia equation that is designed for a hollow cylinder. The two moments from the bending moment stress equation come from the force that's acting on the cylinder portion as well as the billboard portion, and then we take the distances from the center of both of those objects in order to get the complete moment that's acting on all of this. Of course, the force equations for those moments still don't have the velocity term, as that's what we're trying to solve for. So that's when we have to do a little bit of algebra in order to take our failure stress criteria and compare that and reduce everything down in those force equations, the distance from the neutral axis and the area moment of inertia, reduce all of these equations down to isolate velocity. Once we do that algebra and solve for V, we get a final result of 209 feet per second. And 209 feet per second translates out to 143 miles per hour. So if I was a damage surveyor in this instance, I would rate this failed billboard as an EF3. So now that we've looked into some of these damage indicators more in depth, what can we gather as an overall arching statement on the Moore 2013 EF5? I think the first important thing to emphasize here is just how rare it is for an EF5 damage indicator to be assigned. I think in the case of Moore, since we saw over 4,000 damage indicators surveyed and only 9 of them come out EF5, it's a very, very tall task in order to rate something in EF5, and you have to be very clear and concise in terms of what is an EF5 damage indicator. And sometimes it takes that extra guidance in order to officially rate something in EF5. And, you know, in some of the instances that we've seen, like Rochelle, for example, you're working from a smaller pool, and with these high impact tornadoes in heavily populated areas, you have an extremely large sample size, and it becomes much more clear in order to say definitively that something is an EF5. In the case of like the Rochelle Fairdale tornado, you didn't have that sample size, so it becomes a lot more difficult to conclusively say something is an EF5. And that's just one of the shortcomings when it comes to the scale. We've talked about it a lot in these damage analysis videos, that the scale is not perfect. And I think overall we underestimate just how strong 200 miles per hour is, and that there are not a lot of man-made objects that are capable of surviving 200 miles per hour. If you think about kinetic energy increases exponentially with speed. So, you know, the more air you're moving, the faster you're going, it's just exponentially increasing in terms of impact. So, you know, a lot of homes across the United States are never going to survive an EF5. And, you know, you're only going to select a few cases here and there in these very extreme tornadoes where it's very concrete that something is or is not an EF5. So I think sample size and proximity to major metropolitan areas is a big factor, because you're going to have better construction closer to metro areas. That's just how it works. You have more skilled builders in a tightly controlled, populous area, you're going to have so much more resources in order to build things to higher standards. So that's just the nature of it. And I think, once again, we get back to the idea that the rating, though important, is not as important as the overall human impacts, which should be the utmost important aspect when it comes to tornadoes. The human impact is the most lasting impression between fatalities and injuries, and people that may have not been injured but just overall impacted by the tornado. They lost their homes and stuff like that. There's going to be an emotional scar there long after they are able to recover and rebuild their homes. So I think those are important notes to close out on here in the damage analysis of the 2013 Moore EF5. Thank you so much for tuning in and watching this damage analysis. I hope you learned something today. And of course, stay safe out there when it comes to severe weather.